it will create a sort of push. So it will be creating a field which will be pushing the any charge which is placed there away. Of course, the charge which is here will also make a big say change, because if the charge is positive, then it will see the push, and if the charge is negative, then it will see the pull, because our discharge because our discharge that I have assumed is a positive charge. But if we don't have anything here, and if we have just one single isolated charge, then a positive charge, as we have seen here, will create a field around itself, which will be like, a pulling going away, and a negative charge will create a field around itself, which will be like, this is pushing, and this is like pulling. And this is the example we just missed. In this example, what we are doing is, instead of placing the charge at somewhere else, I'm placing the charge at origin. So if I place this charge at origin, and if I have any point which is P where I need to find, and this point P, its position vector is R, then how can I get it? It's very simple. So it is Q1 times R is the position vector where your point of interest is, minus 0. Why? Because our charge is kept at origin, divided by 4 pi epsilon times the modulus of R minus 0 Q. And this is nothing but Q divided by, so I'm now just removing this subscript. So it is Q divided by 4 pi epsilon R square times AR. So what I am doing here, if you see, I have a position vector R bar above, and I have here the magnitude Q, right? So what I'm doing, I'm rewriting this as R bar over your modulus of R. I'm naming it as my AR. This is the definition, right? So AR is nothing but, it is the unit vector, the unit radial vector in the spherical coordinates. So it's R bar, the position vector where your point of interest is, divided by its modulus. So this, if I name it as my unit vector AR, then this is what I'm placing here. This is the unit vector. And since I have the modulus to the power of 3, so 1 is gone here. So the remaining R square is here. Got it? So this is very, very common. We are going to use this in our course several times. So this is nothing but the expression for the electric field due to a point charge which is placed at origin. So it is Q divided by 4 pi epsilon R square times AR. So it will be radial, and this is what we plotted here. Okay. Now, if you have, instead of one charge, if you have several charges in our free space, like Q1, Q2, Q3, Q4, and they are all distance vectors. So this is R1P, this is R2P, this is R3P, this is R4P. If these are all my distance vectors, then the electric field that you will see here at this point, due to all these charges, they will follow the superposition principle. That means it will be the electric field that will be exerted at this point due to Q1 plus the electric field exerted at this point due to Q2, Q3, and so on up to Qn. So if you see here, so the electric field will be the electric field due to charge Q1, which is E1 bar, charge Q2, E2 bar, and so on. And what is this E1? Let's replace this E1 with its expression. So it is Q1 times the distance vector divided by 4 pi epsilon times the distance vector Q. Similarly, we do it for E2 and so on to En, and then we can replace this with position vectors. We have just now done it. So the distance vector is nothing but the position vector R minus R1 and R minus R1. So what is your R here? Your R is the position vector of your point of interest. It is the position vector which is giving you the location of your point of interest. And R1 is the position vector which is giving you the location of your charge Q1. So therefore, this is for charge Q1, this is for charge Q2, and so on. And now we can write it as a summation. So this is equal to summation of, if I have n charges, so it is 1 to n qk r bar minus r bar k over 4 pi epsilon times the modulus of r bar minus r bar k q. Got it? So this is due to several point charges. Now let's take an example. So here the example says now you have 2 point charges, and these 2 point charges are in the free space. One is 5 nanocoulombs placed at 2, 0, 4. Another is minus 2 nanocoulomb placed at minus 3, 0, 5. So now it is in the rectangular coordinates, Cartesian coordinates. And now we need to determine the total electric field or the resultant electric field at this point, which is 1, minus 3, 7. So how are you going to do? So you need to first find the electric field exerted by this charge at this point and the electric field exerted by this charge at this point. Now, what will be the electric field here? Will it be like, what type of disturbance it will be at this point? Will it be a pushing type of disturbance or pulling type of disturbance? It's difficult to say, because now you have the charges, one is positive and one is negative, and they are placed at different locations. So it will be difficult to say. So let's solve it, and then we will get the answer. So it's not so easy to identify the type of disturbance. So what I'm doing is I'm taking the first charge and I'm finding the position vector, which is R minus your position of your charge 5. So this is 1, which is my R, minus the position of my charge 5 nanocoulomb. So it is 1 minus 2 is minus AX, minus 3 minus 0 is minus 3AY, 7 minus 4 is 3AZ. So this is R, position vector R minus position vector R1, and divided by 4 pi epsilon times the modulus of this, which is the mod of this. So it is root of 19Q. So similarly, we can do it for the second charge, and then we simplify it. And if we simplify, we get this as my electric field. So therefore, my electric field has X component, Y component, and also Z component. And to, say just visualize its direction, it's difficult because now you have in 3 dimensions, right? So you have in 3 dimensions. So it's a little bit difficult, but let's try to see whether we can do it or not. So you have minus, so if it is X, Y, and Z, so it is in this direction, is my minus AX, and this is the direction is my minus AY, and the positive direction is my AZ. So, it is something in this, the resultant of all these three will go something like this. So it is in this direction. So this is what I told you. It will be difficult for us to find the resultant because we know that the electric field is a function of the distance. See here, it's a function of the magnitude. It's a function of the distance. Distance of what? Distance between the charge and the point, and also whether the charge is positive or negative. Okay, so let's go to our next lecture. Now, in the last lecture, we looked at only point charges, right? So, charges which are very, very small. And as I told you, you can visualize point charges are the charge that you can place it on the tip of the needle. So you can think that as a point charge. Now, in general, you have point charges, but you also have continuous charge distributions. Okay, continuous charge distribution. So that means charge which is continuously distributed. It is spread, distributed. So the electric field can be produced by this point charges and also by this charge distribution. And the kind of electric field which is produced by these charges or charge distribution is called an electrostatic electric field intensity. So E bar is the electric field intensity. And now I'm using the word electrostatic. Now, why I'm using electrostatic? Because the source which is creating this electric field, which are the point charges that we have taken in the previous lecture, and the continuous charge distributions, they are fixed. They are not moving. The charges, they are static. They are not moving. So that's why the electric field which is created by these kind of charges which are static is called as static electric field. So static electric field means the electric field doesn't vary with time. Okay, it doesn't vary with time because your charges are not moving with time. So therefore, your electric field will also not vary with time. So if you plot the electric field with respect to time, you will get a constant value. So that's why it is called as an electrostatic field. So we have point charges, as you can see here. Now I'm giving an example, point charges, which we have seen. Now you also have charge distributions. Now charge distributions, you know what we did? We simplified the charge distribution. Now, when you are distributing the charges over some, some area, then it's, logical to talk in terms of charge density. And they are classified into three forms: line charge, surface charge, and volume charge. Line charge, it is, its distribution is according to the line charge density, which is called as rho L. So rho is usually used in our Sadiku book to represent charge density. So rho L is line charge density, and its unit is in coulombs per meter. So it is telling you, it's telling you how much charge is available along a line. So, and this is a normalized value with respect to the length. And this is surface charge density, rho S. So normalized over an area, meter square. And this is the volume, and the charge density is normalized with respect to the volume, which is meter cube. And how they look like, you can see here. So this is your line charge density. This is your line charge density. A simple example you can visualize is like a thin wire. A thin wire a metallic wire, and on that metallic wire, you have charges. You have charged that wire, a static charge to that wire. So that will be a line charge. And if its line charge density is rho L, then, and if its length, if its length is L, then how can you find the total charge of this line L? You can take a small, infinitesimally small or elementary small length dl, and let's first find the charge of this elemental length dl. So the elemental charge dq is rho L times dl. So multiply the charge density, line charge density multiplied by the elemental length dl. This will give me the elemental charge dq. And now you integrate that elemental charge dq over the complete length, this complete length. So the total charge will be integral over the complete length L, rho L dl. This will give me the total charge of a line distribution. Similarly, you can get it for a surface. So suppose this is a sheet. You can think it as a sheet. Example is a very thin metallic sheet which is filled with charges, which is charged sheet. That is an example of a, the surface charge distribution. Again, you can find a elemental charge dq by taking it as an elemental surface ds and multiplying it by rho s. And if you integrate this dq over the complete surface, you will get the total charge. And similarly for the volume. So you can take dV, small elemental volume dV, and multiply by rho v and integrate it over the whole volume. Will give you the total charge. So these are the different kinds of distributions. But guys, you can just keep one thing in mind. Can anybody tell me, this line charge and the surface charge, they are these are the special cases. So these are the special cases of which kind of charge distribution? The line charge and the surface charge, these are the special cases of which kind of charge distribution?
Continuous.
Volume.
Volume. It's all the three are continuous. They are all continuous charge distributions, right? But this line and the surface, these are the special case of volume, as your friend said, right? It's correct. These are the special case of volume distribution. So volume distribution is actually the main kind of charge distribution. And from here, the special case is if one dimension becomes negligible, it becomes surface. And if two dimensions becomes negligible, then it becomes line. So these, we use it to simplify our analysis. And as I told you, a simple example is a wire. A wire can be considered as a line distribution. We do not need to go and look at its volume and other things until and unless it is thick. And then a sheet, a thickness of a sheet is very, very small. So although in reality it's a volume, even a sheet is a volume. But since its thickness is negligible, we can assume it as a surface charge distribution. Okay? Now, we are now generalizing the electric field at a point P due to different types of charges and charge distributions. So in a room, if you have some point charges, but also if you have a charged wire somewhere, or if you have a charged sheet somewhere, or if you have a charged volume, so, a charged sphere, a metallic sphere which is charged, then if you want to find the electric field here due to all these charges, these point charges and this charge distributions. And they are all static. They are not moving. The charges are not moving. Then again, at the point P, you can easily find by using the formula, the superposition principle. So you individually find the electric fields for all of them. So if you see here, the electric field at an observation point P is first summation of all the point charges. This we already derived. So it's summation of 1 over n, assuming n point charges, qk over 4 pi epsilon. This is the distance vector of each charge, and this is the magnitude of that distance vector q. So this is the electric field due to point charge. Now, what will be the electric field? What will be the electric field due to this line charge? The electric field due to line charge? The electric field due to line charge, we will follow a very similar expression of, that we got it for the point charge. What it is? It is, see, integral over L, rho L dl over 4 pi epsilon times r bar over r cube. Where what is your r bar here? This r bar, if you see, is my distance vector from this elemental length, which is situated on the line charge, to the point of interest. Again, the direction is very important. Remember, the direction is very important. Based on the direction, we derive the Coulomb's law. So the direction is always the distance vector will point from your charge or from your line charge, point charge, or volume or surface charge to your point of interest. So based on that, we derived this expression. So we need to be careful. So our r kp bar, the distance vector, is always pointing in this direction from your charge to your point of interest. So here also we follow the same thing. From your elemental dl to the point of interest is your r. From elemental ds to your point of interest is r. And from elemental dv to your point of interest is r. These r are different, okay? It can be different. I'm just representing it as r, or if you want, you can make this as rl, you can make it as rs, and you can make it as rv. So what will be the electric field due to the line charge? If you see here, it's now integral rho L dl over 4 pi epsilon times r over r cube. And this integration is important. Why? Because we want to find the electric field due to the total charge which is carried by this line. And the total charge which is carried by this line, I can only get with the help of integration. So that's why I have an integration here over L. Similarly, for surface charge, it is rho integral over the surface, rho s ds over 4 pi epsilon times r bar over r cube. And for dv, or for a volume, it is integral over v, rho v dv over 4 pi epsilon r bar over r cube. So these are the expressions that you can use to find the electric field due to a line charge, surface charge, volume charge. This is the general expression of the Coulomb's law for the line charge, surface charge, and volume charge. And this is for the point charges. Okay, yes, Taha.
Doctor, for example, if we are talking about the line charge, because the sample will change every time, does that mean the length will change also? The
sample, can you just elaborate?
The DL.
Sample?
DL will change because it's integral.
Yeah, the DL length will not change, right? So you will...
the position of DL will change. Does that mean the R will change?
Yes, this R now, that's a very good question, Taha. guys, we will look at this in our example, because our R will no longer be a constant, Taha. Now our R will become a function of your spatial coordinates, because as you mentioned, when your DL changes, so your R should change, right? So therefore, your R will no longer be a constant. It will be a function of your spatial coordinates. Got it?
Yes, yes, thank you.
Okay, when we take the example, it will be clear for you. So this is the expressions for the electric fields. Now let's take the example, and with this example, it will be more clearer, what Taha has just now asked and what I have explained. So now what is the question? The question is, we need to develop an electric field expression or electric field intensity expression. And by the way, guys, now throughout this course, I'm going to use the word electric field and electric field intensity as I like, okay? But remember, even if I say electric field, to be precise, it's the electric field intensity. So electric field, we need to develop an electric field E due to an infinitely long straight line. So we have a straight line which is infinitely long, and it has a charge it's a line charge. That means it is carrying charge, and it is line charge according to a uniform charge density rho L. So rho L here is the uniform charge density, and it's a line charge, and it is infinitely long, and it is straight. Okay, that's why I underlined these. These are very important. It is infinitely long, it is straight, and it is uniform. Okay, so how does this looks like? So if you see here, this is our problem statement. Now, what you are seeing here, you are seeing that, let me just make it a little bit. Guys, you are able to see my sticky note, right?
Yes.
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 Yeah, because I will be drawing on the sticky note as required. So if you see here, this is my problem statement. Now, what I am doing is, this is my line charge, and it is infinitely long. So here it is going to minus infinity, and here it is going to plus infinity. Okay. Now, I have placed this line charge on the z-axis. I have placed the line charge on the z-axis. Now, I am taking P as my observation point. So P is my observation point. And now my objective is to find the electric field of this infinitely long, straight line charge carrying uniform charge density rho L at this observation point P. Okay, so this is my observation point P. Now, to do this, first, because it's we need to do it mathematically, so we need to define some terms, the elemental length and the position of the elemental length from the origin. This is required for us to do the integrations. So now this is the small elemental length that I'm choosing. So this is the small elemental length. Now, instead of using DL, I'm saying it DZ dash. Why? Because my line charge is placed along the z-axis. Okay, so this is DZ dash, and I'm assuming that this is currently at a distance of z dash from origin. Okay, so this is at a distance of z dash from origin. And now if this elemental length is dz dash, then what will be the the elemental charge of this small elemental length, the elemental charge dq will be rho L d. And from here is the distance vector r, which is pointing away from the elemental charge and towards my observation point P, which is r. And also, I'm assuming that this observation point P is at a distance of rho from the origin. So these is our problem statement, that these are the conditions. Now, which coordinate system I'm using to solve this? As you can already, you can already say, looking at this row, I'm going to use the cylindrical coordinate system. And you will know why I'm using cylindrical coordinate system once we solve this. So this is my problem statement. So now, as you can see, let's solve this. So let me draw it. So this is my infinitely long charge. By the way, it is straight, please. Okay. So this is the origin, and this is my point P, and this is rho, and this is my vector r, and this is my dz. Okay, and this distance is z dash, which I have assumed. Okay, and this is my line charge. So in order to just show that it's a line charge, I'm putting it as a some lines on it, just to distinguish between just a line and a line charge. Okay, now if you see here, let's start. So what we are doing. So this is my electric field expression. See, electric field expression, integral over L, rho L dl over 4 pi epsilon r bar over r. Okay, now we need to find this distance vector r. Now the distance vector r, as you can see, I need to find this vector, right? I need to find this vector. So what I'm doing is, I'm finding this vector with the help of these two components, this component and this component. Got it? So if this is rho, and this is the cylindrical coordinates. So in the cylindrical coordinates, so just to show you, if this is my cylindrical coordinates, so this will be AZ, right? And this will be my A rho, right? And my A theta will be like this. This will be my A, not theta, A phi. So I hope you recall this, right? Cylindrical coordinates that we have already discussed in the first class, right? So therefore, if this distance is rho, can I represent this as a distance vector? Yes. So it will be, so this will be represented as a distance vector. So it will be rho A rho, right? It will be rho A rho. This will be rho A rho pointing in this direction, and this will be Z dash AZ pointing in this direction. So this vector will be rho A rho, and this vector will be Z dash TZ. Z dash AZ. Now, can I represent this distance vector R in terms of these two vectors? Yes. The distance vector R is, this is the direction of rho A rho. So I have to go in this direction. So minus rho A rho plus Z dash AZ will give me R bar, the distance vector. So rho minus rho A rho minus rho A rho plus z dash az will give me the distance vector.
No, it should be the opposite.
No, see, this is the
Minus
direction
z
of r.
dash.
Yeah, this is the direction of r, and this is the direction of my z dash az, right? And this is the direction of my rho arrow. Right, my friend?
Yes.
Okay, so I want to find this r. So I need to go in the opposite direction here. So therefore it is minus rho arrow and along the same direction. So it is plus z dash az. Clear?
Okay.
Okay, so this is how I can find this distance vector, and this answers Taha's question, because now your r becomes a variable, because as dz changes, your r should change. So therefore your r has now become a function of the spatial coordinates. Okay, it has become the function of a spatial coordinates. And also remember one thing, in Sadiku book, we always represent the position of the charge or position of the, any charge. We always denote it with a prime. And that's why you see, I have used this as Z dash, and I have named this as DZ dash. So the reason is always the line charges, they are not line charges, any charges, they are all represented by primes. Their positions are represented by primes. Okay, so we got this. So it is rho arrow minus z dash az. And now what is my dl? We have seen here. My dl is nothing but is
dz dash.
dz dash, because my line charge is placed along the z-axis. It is placed along the z-axis. And this is, so, okay, so let me not erase it. So this is r bar, and this is my origin. This is rho, and this is z dash. So this is dz dash. Now substitute these two here, and that's it. So you always need to find dl and the distance vector. So now when I substitute here, so you see, and what is the units of my z? Because you are now, when you substitute everything here, you are seeing that you are integrating with respect to dz dash. That means you need to integrate your complete line. Now since your line is infinite, so therefore the integrating ends are minus infinity to plus infinity. The limits are minus infinity to plus infinity. Now this is your integral. So now let's go to the mathematics, and then you can find the integration. We can separate these two terms, the term of arrow and the term of the unit vector az. So if we separate these two and do the integration, so we will get this for arrow and we will get this for az. Okay. And now if you see here, for this term, we are doing the integration with dz. That's why rho becomes a constant. So if you see, there is a rho here. Rho becomes a constant. So that's why I can take that rho outside. And arrow is your the
Unit vector.
Unit vector, so which is here. Now for this one, it is minus z dash az. So minus is here. Z dash d, az is here. Dz dash, the remaining terms are here. So you just do the integration of these two. Now, if you do the integration of these two, you will see that the az part will cancel. You will get this answer as a 0. So your az component vanishes. and the integration of this will become 2 over rho square. And if I simplify this, then I will get the expression for the line charge of infinite length and straight as rho L over 2 pi epsilon rho L. Rho L over 2 pi epsilon rho L. So that means at this point, I'm only seeing one component. And what is that component? So my point P will see the electric field, and it is only one component. What is that component? A rho. That means it is in this direction. A rho. AZ, no, cancelled. A phi, no. A phi is not at all there. That means your problem or your line charge, it is independent of the phi plane. So only this is my field, whose magnitude is rho L over 2 pi rho. That means it depends on the charge density and also the distance of my observation point from the origin, which is rho. So if this increases, then my magnitude of my electric field goes down. Now, if you see here, just some observations here, and the observations are that it has only a rho component. Your electric field has only a rho component. Your A phi component is cancelled. Your AZ component is cancelled. Now, why your AZ component is getting cancelled? You can visualize this easily if you want. Even without, say, solving that integral. You can think from the following point of view, guys. See, now this is an infinite line, right? So the line is going infinite. Now, think this small elemental length, it is giving us a charge of dq dash, right? Now, and this is at a height z dash. Since it's an infinitely long line, you can assume that you have a small same elemental length dq dash at the negative side, and which is also again at a same height. So if this is a small charge and this is also a small charge, then let's not now forget that this is a line. Let's just think that this is just a charge. It's a charge here and a charge here. And we want to see what will be the electric field of this charge at this point, this point. So if this is my charge, its field will be, like this, right? Am I right? Because it is dq dash, its field will be like this. Agree? See, point charge, we have seen that its electric field will be radial, right? So it will be everywhere. But since we want to see it at this point, so I'm just trying to find what will be the electric field of this point charge at here. So it will be in this direction. Okay? Now, what will be this charge field at this point? It will be in this direction. So what will happen if I decompose this electric field? I will get a component in this direction. I will get a component in this direction. And for this one, I will again get a component in this direction and one component in this direction. Now this component and this component, they will be equal in magnitude but opposite in direction. Why? Because these two charges are at the same height, and therefore, and this point is the same where you are observing. So this and this will cancel out, and only this will stay, which is nothing but my A rho. Now this I am doing it only for this small thing. Now since it is infinite, we can say that for any charge, for any small charge which is here, there will be an equal charge which will be present here. And again, when you look at these two charge effect at this point, they are Z components will cancel. And if you take one charge here and one charge here, again, they are equal. At this point, their Z components will cancel. So like this, you can think that your line charge is made up of several small point charges. But for each point charge above the origin, there will be a point charge below the origin. And when you look at these 2 point charges effect at this point P, the Z component will cancel, and therefore only A component will appear. Got it? Clear? This is the property. Anything? Yes. Is it clear?
Clear, doctor.
Clear? Okay. So I think the time is up. So this is our line charge expression that we derived. But there is just one point which I want to emphasize before concluding, is that, you know, all our derivation is valid because our line is straight. If our line is not straight, then this will not be valid. Because if the line is not straight, then the integration becomes more complicated. You have to divide the line into different parts and then do the integration. So remember, that's why infinite, straight, and uniform, all these three are important. Okay. So we will stop here and